Okay, so let's hi everybody, let's start the second lecture. Well, this is where we actually finished the first lecture. But let me just very quickly go back over what we did in the first lecture. So just to remind us. So there is this. We were thinking about integrating out. Well, first of all, one second, let me just. Yeah. Okay. So we were thinking about how to calculate certain terms in the effective action involving powers of the graviphoton, and we were thinking of how to get those from integrating out charged states under the graviphoton, using these terms in the action. If we look at the coefficients, we can define this function here, and this function is what we call the topological string free energy under an identification of the graviphoton background with the topological string coupling. So this gives us a way to calculate the topological string free energy by integrating out states, looking at how they generate these terms in the effective action, and then from there we can read off the topological string free energy. The integrating out calculation was basically following the idea of Gupper, Kummer, and Raffa, and essentially integrating out states, much like in QED with the Euler-Heisenberg-Lagrangian, and you generate these higher terms in F or higher terms in W by integrating them out of one loop. And then we just went through the integrating out calculation, very standard quantum field theory analysis. But there were some subtleties. The main subtlety is to do with the fact that the graviphoton background has to be imaginary. This is because if we wanted the 5-dimensional metric to be real, we had to choose the graviphoton to be imaginary. There was a subtlety that I didn't have time to go into in the first lecture. Maybe I'll just quickly talk about a little bit about now, to do with when you calculate, when we integrate out, in the Schwinger integrating out calculation, we have to take this trace of the Hamiltonian, and this is a trace in the background of the graviphoton. And this is like a standard calculation where you sum over energy eigenstates of charged modes in a constant magnetic background field. That's a standard calculation, except that in the standard calculation, you have electric charge and you have a magnetic field B. And in our case, we have the charge, which is Z bar, is complex, and the background field, which is the graviphoton, is imaginary. So it's okay. It's the same as the standard calculation, apart from the fact that instead of EBH, which is real usually, this thing is now complex. So that leads to some subtleties, but there are ways to get around it. And so I'll just mention those a little bit in a second, how to get around it. But apart from those subtleties, you can then just perform the trace over the Hamiltonian. And then once you perform a trace over the Hamiltonian, you get this 1 over sine. And this is the final result that we get. That's where we're going to start from that's where we're going to start the second lecture from. And that's actually essentially the starting point of the research paper that I wanted to discuss. Are there any questions about how to get to here? I don't know if people were in the first lecture. So before so this will be my starting point now, this expression here. But before that, let me do this aside, which I mentioned, to do with the subtlety of this electric yeah. So as an aside, the subtlety to do with the fact that when you want to do the trace over the Hamiltonian, so you have to sum over the energy eigenstates, then it is a standard calculation, but under the identification where essentially we have to equate the charge with the charge with Z bar and the electric fields with the graviphoton field, which is not, so this thing is complex. So this thing is complex. Well, this thing is real. So we can't quite read off the results, but there is a kind of nice trick you can do to show that the calculation is just a standard one. Okay, so the trick you can do is that this trace of the Hamiltonian, remember, is inside an integral like this. And what you can do is you can, we'll do this trick actually also in later on in the talk in a bit, is you can define, so we define U, which is S times Z bar. Okay, so that's now a complex parameter. And we absorb S into the Hamiltonian and now write it as a function of U. And so this becomes an integral du over U in a complex parameter. Trace e to minus S, S now. H tilde of U. And the integral in the U plane is over, in the U plane is now over a straight line because remember S was the real parameter and we now just we multiply it by a constant complex number. So this essentially over some straight line in the U plane where this angle here is the angle of Z bar. So Z bar would be of this form. And when we do this change of variable, then before we had EBH equals Z bar W1 2 minus, but now we've absorbed S into the Hamiltonian, we find that one finds that you find S times Z bar here, which is just U, like this. So again, we still have this issue that on the right-hand side, we have something complex, and on the left-hand side, the standard calculation is for a real magnetic background field. But now what we can do is the following. Since this is a calculation in the complex plane, we're allowed to modify the contour, the integration line as we wish. And we're allowed, as long as we don't cross any poles, in particular, we can rotate it to the imaginary axis and do the integration along the imaginary axis. As long as we don't cross any poles, that's okay to deform the contour this way. And indeed, we'll show that the only poles that one has actually are on the real line. We'll do that in a second. And so this is an allowed deformation. And then if U is imaginary, so this is imaginary, and this is also imaginary, this is the graviphoton background is also imaginary, and therefore the product is going to be real. And now we do the calculation where EB is real, and that means we can do the standard calculation of a charged particle in the background field. We get the result that we want, and then if we want, we can rotate back to the original line, or we can leave it unmodified as we wish. So that's the trick that one has to do. Apart from that trick, the calculation to get to this point is very standard. Okay, so let me write out again the formula that we got to. And are there any questions, by the way? No. Okay, then let me write out again the formula that we got to, and we'll go through the different things in it again. Yeah, so the formula that we find after the integrating out calculation is that, is this what I wrote? F of t is sum over beta r and alpha r beta. Sorry, yeah. Integral. Okay, so it's like this up to infinity ds over s, and then we have the central charge parameter here, and to this and the part on the bottom like this to r. And the central charge, remember, is well, in general, if you have multiple parameters, takes this form here. Okay, so this is just what I wrote before. So we'll carry on from here. Are there any questions about this result here? That's going to be our starting point. This is what we spent the last lecture getting to, basically. Okay, so let me first of all comment on one thing here. There is actually divergence at s goes to 0 here. And what actually is done is that we have to put a cutoff here on this integral. That's just an ultraviolet cutoff in a one-loop calculation. Because s is the Schwinger proper time, that's the time that it takes the particle to propagate from the initial point to the final point. And if s is going to 0, that means it's propagating very fast. So that's the ultraviolet. So we're just putting an ultraviolet cutoff on the calculation, and epsilon should just be bigger than 0, but can be very, very close to 0. Yeah. Sorry. So this is the cutoff that we put here. And this expression is very similar to the expression that's in the paper by Gobekoma and Vafa. But it's not actually what's in that paper, and it differs slightly. Well, in an important way. So, and the difference between this and the expression of Gobekoma and Vafa is essentially the content of our research paper. And that's what we're going to be discussing. Yeah, so let me just summarize this. Okay. Okay, so let me first explain what is usually done, or let me go to the usual Gobekoma and Vafa form and see what is usually done in the literature, and then I'll explain that a little bit, and then I'll talk about why the results should be different than that. Okay, so what is now usually done is that, so let's do the usual Gobekoma and Vafa. Let's get to the usual Gobekoma and Vafa formula. That's what we want to get to, and see how we get to that. So what is usually done is that one can consider a rescaling. S goes to S times Z bar beta n. Okay, so if we rescale that, you can see where S, here we have SS bar. Oops. Wait, how do I do this? Okay. Yeah. We have SZ bar here, okay, and we have an SZ bar here. And so after you do that change, we can write, let me just not do it here. Yeah, then you can write as the sum alpha r beta integral epsilon ts over s. And then at the top, we get S Z beta n. And here we have 2 sine S lambda over 2 to the 2 minus 2r. And this is a kind of nicer expression in the sense that now we see that manifestly it's holomorphic in the t parameters, which is something that's expected. Okay. But this transformation is not quite correct because you see that the important point is that we have also here the integration range. And if we do the change of variable, then we also need to change the integration range. And as I discussed before, under such a change of variable, we will need to change the integration range to lie in the complex plane. But if we don't do that, if we don't change it to lie in a complex plane, then we will write an expression like this. And this is the way that the Goodman-Common expression usually comes about. And you can, this is how you would find it in research papers. You can do another simple analysis, which makes it a little bit simpler. Let me just go through that. If we remember that Z, let's consider just one parameter t. So this is beta t plus 2 pi I n. Then if I put that into the expression, then then I have s beta t, and then here I have minus s 2 pi I n divided by 2 sine s lambda over 2 to the 2 minus 2r. And now I can use Poisson resummation to write sum n equals minus infinity to infinity. That's the sum over n of e to the 2 pi I n s. That's what we need to do. That's the sum that we're doing here. Okay. Then that's equal to the sum over these delta functions like this, where k are integers. This is Poisson resummation. And so if I put that into this integral, I'm just going to get that this is equal to the sum now just over beta and r times the sum now over k of these integers, alpha r beta. And then I have these delta functions, well, s minus k. And now the e to the 2 pi ns is gone. Like this. And now it's very easy to do the integration because it's just delta functions. So then we obtain the result that this is sum over beta r and k of alpha r beta. And then we just evaluate at s equals k. So 1 over k e to the minus k beta t divided by 2 sine k lambda over 2 minus 2r. Okay. So this is just a simple way to do the integral using Poisson resummation. And this is usually the way that you find the Goodman-Common expression in most research papers, as a sum over integers, right? And these are the Goodman-Common invariants. Okay, are there any questions? Okay. Now this form of the expression shows a little bit some of the issues. Yes. Oh, so there's any question, I think. Yes, beta and r positive. Sorry. K is integer. Well, K is also positive because K is positive because the sum here is over negative and positive K. Okay. But when we put it into the integral is only over positive s. So that means that we're only going to evaluate the delta functions on positive s's, and so positive k's. Okay. So that means that here k is also only positive. It's actually bigger than or equal to 1. We don't have the k equals 0 piece. Oh. All right. Okay. So that's the Gubic-Rafa expression for the free energy. Now, one can see already there are some issues with this expression. One of the issues that we see is that so this is an expression where we can expand the sign k lambda over 2 for small lambda. Okay, and then we get a series in lambda. And this should be treated as what's called an asymptotic series. In other words, this expression here is not well defined in general for finite lambda. We should really think of it really as an asymptotic series as lambda goes to 0, term by term. So one way to see this, in other words, this expression is a sum over terms, is not necessarily convergent. And one way to see this is, for example, if we see that if lambda is, let's say, a rational number times pi, then sine k lambda over 2 is going to go to 0 for some value of k, right? Because lambda is rational, and so, sorry, times 2 pi. Well, doesn't really matter, but okay. Let's write this q times 2 pi, okay? So, I mean, let's write it explicitly here. Let's say lambda is some integer m over some integer n times 2 pi. Then it's clear that for the value where k is equal to n, we're going to get sine of m pi, which is just 0. And if we're going to get a 0 with a sign, then this thing is just going to blow up. So we're going to get, if r for the r equals 0 contribution, we get 1 over 0, and that's an infinity. So those terms, all those, there's in fact an infinite number of infinities, because that's true for any k that's a multiple of n. And so this series will blow up if lambda is rational in terms of 2 pi. So those are kind of situations that are telling us that this series really should be thought of as an asymptotic series, valid only for lambda equal to 0, essentially asymptotically approaching 0. Rather than thinking of this as an actual convergent function of lambda.
Can I ask a question?
Yes.
So, but for, I mean, it is a problem only when 2 minus 2r is greater than 0, right? Like for a small genus 0 and 1.
Yeah. So for r bigger than 2, this problem doesn't arise. Yeah.
Yeah. Okay.
Okay. Yeah. So this divergence comes from the r equals 0 part. But that's just an example. You can also, there are people who study this series, and there's various problems with it. I think in general, it's considered only as an asymptotic series, this expression. And the idea is that this series is not really the complete expression for the free energy, but it's expected, the expectations are that there are additional contributions that are missing from that expression. Additional contributions, and those additional contributions are non-perturbative in lambda. So they would go like e to the minus t over lambda. So non-perturbative. And then there's many people, many papers. I'm not really an expert in this field, who try to get these non-perturbative contributions by trying to study how this perturbative asymptotic series behaves. And this is a field called resurgence. Resurgence tries to get these guys from the perturbative series, but I'm not really an expert on that. There are other ways to just show that these things are there using dualities from Chern-Simons theory and things like this. But in general, we don't know how to calculate these non-perturbative contributions in general for a general Calabi-Yau. But there is a lot of work in trying to figure them out in certain settings. So okay, so that's the Guber-Kummer-Waffer formula, and these are some of the issues that come up with it. Are there any questions about this? Okay, so but now if we but remember, I told you that this is not really a correct thing to do. If you do this rescaling, you need to be careful. You need to also change the integration range. And that's what we're going to do now. And we're going to see that this is going to have a very important, this is going to lead to a very important difference from the usual formula. Now, I should say it's not really the case that this formula here was known or used, and then it was only then there was a change of variable, and then this was kept the same. That would be a little bit too easy thing to have missed. But there were various rotations in the complex plane that were done before the rescaling, after the rescaling, and so on in various different papers. So whatever happened, this is actually the expression at the end this was the expression really that was used in the literature until a few weeks ago when we wrote our paper, and where we proposed that this expression that this is not correct, and that in fact this expression is the correct one. Okay, and I tried to derive this expression in these lectures from very basic principles and analysis. So that was the point of it. But once you get to this point, this expression here, if we accept this expression, then we will see that this is really radically different from what has been done so far, which uses this expression, just because you have to change this integration range. Okay. So now let's go back and let's do the change of variable a bit more carefully with the change in the integration range, and we'll see what happens. Okay, so let's start again. Let me write down the expression again. So okay, so by the way, we will take this cutoff to be 0 plus. That means it's arbitrarily close to 0, but doesn't include the 0 itself. Okay. So and we'll consider a single vector multiplet for simplicity. So that means instead of ti, we just have one t. That's all the thing that's important. And also for simplicity, we'll consider a single Guber-Kummer-Waffer invariant to be non-vanishing. We will see later how to generalize it for more general cases. So we'll consider only that alpha 0, 1 is non-vanishing and 1. And everything else is just 0. Okay, so in this case, this is actually known as sometimes as the resolved conifold case. Conifold. So it's what happens in a specific background, which is what's called a resolved conifold. It's an S2 over a cone. So to remind us, I'll just call this RC, but essentially it's just a special restriction. So now we don't have, because all the Guber-Kummer-Waffer invariants are vanishing apart from this one, we don't have this sum over beta and R, because we just have one thing that's non-vanishing. So we have a much simpler formula. It just looks like this. Sorry. There's no beta anymore. So it's just a sum over n squared like this. 2 sine s z bar n lambda over 2 squared. Where Zn is just t minus 2 pi in. Sorry, plus in. Okay. Are there any questions about this? So it's just a very simple restriction for setting. So now what we're going to do is we're going to do it, the rescaling. This is the same rescaling that I discussed about here. Sorry, where's the rescaling? Yeah, the rescaling that's usually done, this one. But we're going to do it a bit more carefully, okay? So what we're going to do is we're going to rescale. And so we're going to define a new complex variable u n, which is s times z bar n. And so now the free energy is sum over n. Well, let's write it out explicitly from minus infinity to infinity, integral. And now we have du over u e to the minus u zn divided by 2 sine u lambda over 2 to the 2 minus, sorry, there's no 2 squared. Good. But now remember, we have to change the integration accordingly. So we have this 0 plus, that's our epsilon cutoff. And we have to integrate over this line here, infinity I theta n, where what is the integral over infinity? So I infinity I theta n mean. That means we have to, if we think about the u plane here, then we have to integrate over a line like this, where this is the angle theta n, and what is this angle? Well, u is s times z bar, so that's s. And then if I write things out, if I write t, remember t is v plus ib, and so z bar is t bar v minus ib. And now, oh sorry, I think this is being minus. Sorry, let me just correct that. So it's a minus 2 pi in, and so now it's a plus 2 pi in here. And then I can write this as s times v plus I 2 pi n minus b. Okay, and so the angle theta n is then just inverse tan of the imaginary part over the real part. Okay, so that's the angle that we have to integrate over. Are there any questions about this? Okay, so now we're doing an integral. We're not doing it along the real line anymore. We're doing it along this half line in the u plane, going at an angle theta n. Okay, now let us restrict for simplicity for now lambda to be real and positive. Okay, so that's the coupling, the topological string coupling lambda, which appears here. Then we can ask, where are the poles in the u plane of this expression here? Well, we see that the poles are if lambda is real, then they're along the real line when u is equal to 2 pi over lambda times a positive integer. So we have poles for u equals 2 pi over lambda times some positive integer. right? Because when u equals 2 pi over lambda times a positive integer, we get sine of 0, which gives us a pole, a second order pole. So that means that we have poles along this real line here in our integrand. So these are the poles that we have all along the real line. Are there any questions about this? Okay. Okay, so now if we think about the free energy, the full free energy, we have a sum over n's from minus infinity to infinity, and each n is going to have a different angle for this line. Okay, and if let's say b is positive and small, then we can look at this thing here. Then we will see that all positive n's would give us positive angles, and then all negative n's would give us negative angles. Okay, so if when we think about the full free energy, then the full free energy is going to be something where in the u plane we're going to have now a sum over integrations along infinite number of angles here. So this will be all the, let's say, theta n bigger than 0. And then also a sum over these integration lines here. Infinite number going all the way here, which will be all the theta n less than 0. And the poles are going to be sitting in the middle along the real axis. Okay, so that's what happens because this change of variable, importantly, is a function of n. Okay, so we're just going to be doing the integration. When we do this sum, each integral in the sum is going to be along a different line in the complex plane. Are there any questions about that? Okay. Now, as I said, if you have a holomorphic integral in the complex plane, you're allowed to deform the contour, but as long as you don't cross any poles. Okay, so if we want to, we can, which we will do, we can deform the contours. We can deform the contours of integration as long as we don't cross any poles. Which means that the best that we cannot bring all the lines together because there are poles in the x-axis. So the best we can do is bring all the lines in the top half plane onto the same line, integration line, and all the lines in the bottom half planes onto the same integration line. So the best that we can do is do something like this. Now we have this integration line. This can be some arbitrary angle theta plus. And then we have this integration line here. That's some other arbitrary angle theta minus. And the poles are going to be in the middle. And they're going to stop us bringing all of the integration contours on top of each other. Are there any questions about that? All right, so then we can write the free energy as a sum of two pieces. I mean, as in the following form. We have the sum over all the n's such that the angle theta n is bigger than 0. Those are going to be integrated over the same contour that we'll call e to the I theta plus. That's the yellow contour. Okay, maybe I can even do this in yellow. E to the I theta plus. Okay, and then we have the integrand. This. And then the other all the other n's are such that the theta n is less than 0. We have to write them as a different integral because their second integral has to be over the red line. So that we have to write as e to the I infinity e to the I theta minus. So it's the same integrand, but we have split those the sum into two, and now each one of those is over the same line. Each half is over the same line. Are there any questions about this? All right. So now what we want to do is perform the sum over n. So before, if you remember, what we did was we did a Poisson summation. We summed over all the n's, and then we've exchanged them for delta functions. Now, it's not quite as simple as a Poisson summation. Well, or maybe it's simpler. We'll see how to do that carefully. So now we want to do the sum over n's. But remember, we can only do it along either the yellow line or the red line. We can't sum both of them together. We have to sum all the n's over the yellow line and then all the n's over the red line. So we have to do something. We want to calculate something like this: the sum of the n's such that, let's say, all the angles are bigger than 0. So that's the yellow line. And then we want to sum this thing here, e to the u z n. Let's see, how do we do this? How do we do this sum? Well, let's write this out. This is equal to sum over n e to the minus u, and then we write out this zn, v plus I. Okay, sorry. Let me just, there's a step we should introduce here. Okay, so let us introduce some notation that will help us do this sum. Okay, the notation we need to introduce is the following. Remember that T, remember, is V plus IB, okay? And what we're going to do is we're going to write B as some integer NB times 2 pi plus a B tilde, such that the integer is just going to be the floor function of B over 2 pi. So that means it's the smallest integer. The smallest integer, we're going to look at the smallest integer such that the next integer would be higher than what B is. Okay, and then B tilde is what's left over. So B tilde is now just between 0 and 2 pi. Okay, so we just write B as some integer plus a little bit, which is between 0 and 2 pi. If we do that, and then we look at this sum that we are trying to do here, so let's write out this sum. So sum n, theta n bigger than 0. And then we want to write out this Zn explicitly. So that's going to be V plus IB. But we can write B like we do here. So let's do that here. So it's V plus IB tilde, which is between 0 and 2 pi. And then we have minus 2 pi I n. That's the minus 2 pi I n inside Zn. But then minus NB, which is this integer associated to B. Are there any questions about this? Okay, so remember, yeah. And then we can just factor out the part which doesn't depend on n. So we can write this like this, V plus IB tilde. Now we have the sum. And we have the case when n minus nb is equal to 1 up to infinity e to the 2 pi I u n minus nb. Okay, so all I did was just, because this is an exponential, I can take this n minus nb and raise it to the power here. And then you get h to the plus I mu. And then here, I have just used the fact that theta n, after this change of variables, is, sorry, sorry. So theta n bigger than 0 means that you need the imaginary part of u bigger than 0, and that's just a statement that if we look at the sorry, let me explain this a bit better. Yeah, so the sign of theta n is just the sign of 2 pi n minus nb minus b tilde. Okay, so that means that theta n bigger than 0 is implied by n bigger than nb. And so we have to just start from here, n minus nb equals 1, and then all the higher n's. Okay. So that's just, we just wrote the sum of the theta n there. And now we can do this. This is just a geometric series. So we define chi is e to the 2 pi iu. And one can check that chi is such that the real part is that this series is convergent. Just because if you're integrating over positive thetas, then you know that the imaginary part of u is positive, and so e to the 2 pi iu has a negative as this is convergent, and so we have a series which is like this. Sum of m equals to 1, because that's where we start from, n minus nb equals to 1 of chi to the m. And this you can write as chi times the sum from m equals 0 to infinity. And then that's just equal to chi over 1 minus chi. Therefore, the sum is just the sum of n minus nb equals 1 to infinity of e to the 2 pi iu n minus nb is just this geometric sum. So that's e to the 2 pi iu divided by 1 minus e to the 2 pi iu. And then that's just equal to so that's just equal to 1 over e to the minus 2 pi iu minus 1, which is minus 1 over 1 minus e to the minus 2 pi iu. Okay. So the final result of doing the sum over just the top line, so the sum over n such that theta n bigger than 0 of e to the minus u zn is just minus. We have to remember this factor we factored out before. Like this. Or if we want, we can write this as minus e to the minus t minus 2 pi I n b u divided by 1 minus e to the minus 2 pi I u. Like this. So that's this. So we did the sum of n on the yellow line, on the top yellow line here. Okay. Now we need to do the sum of n over the bottom line. That's this part of the integral of this sum here. As you can imagine, the result is going to be very similar, but there is one crucial difference. So the sum over theta n less than 0 starts from n minus nb equal to 0 rather than 1. Because b tilde is positive, the way we split it is that with the sum of an infinite number of n's, so we start from n minus nb equals 1, and then all the either n's, and then from the ones at the bottom, we start from n equals to nb, and then all the way down to the negative n's. And that means that when we do the sum, so in other words, theta n less than 0 means n is less than or equal to nb, rather than what we had before, which is n bigger than nb. And that means that when we do the sum, so this is now the sum at the bottom, theta n less than 0, then that's just the sum of n minus nb equal to 0 up down to minus infinity. So n is getting more and more negative. And when we write the sum over a geometric series, the geometric series is not going to start from m equals to 1, but from m equal to 0, because we start from 0 now. And so we're going to get something like geometric series m equal to 0 up to infinity, e now to the minus 2 pi iu. So I've just exchanged the instead of a plus, a minus, because we're integrating down to negative ends. And now, because this starts from 0 and not from 1, we're just going to get 1 over 1 minus chi. So, so that means this thing is going to give us, sorry, let me just write the full answer. So we have this factor outside, remember, eta minus u v plus I beta tilde. And that's going to then give us e to the minus u v plus I beta tilde. And now 1 over 1 minus e to the minus 2 pi iu. Okay, so this thing here is just 1 over 1 minus chi, as opposed to before when we had chi over 1 minus chi. Okay, the difference between the two is just a minus sign, but its minus sign is going to be important. So now if we write the two sums together, so the full free energy expression, we have that the energy, the free energy is now integral. We have the 0 plus to infinity e to the I theta plus du over u. And then we have e to the minus t minus 2 pi I nb u over 1 minus e to the minus 2 pi iu. And there is a minus sign here because we had a minus sign in the integral along the top line. And then this is times 1 over 2 sine u lambda over 2 squared. And then we're going to get the other contribution, which is now over the bottom line. So now this is over theta minus. And it's going to look basically the same, except it's not going to have this minus sign. And then okay, so the difference between the two is this minus sign. But the integrand is, and so we can take this minus sign outside the integral, and we can say that we have the integration is minus integral from 0 plus to infinity I theta plus the integral from 0 plus to infinity e to the I theta minus. Okay, so this is what the integration looks like in the u plane. This is the integration like here, but it's going backwards because it has a minus, and this thing doesn't have a minus, so it's going forwards. And the important thing is now the integrand is the same over the two lines because we've done the sum over n. There's no sum over n. We're integrating the same integrand. We've just taken this minus sign out, and now the integrand is the same over both things. So we're just integrating the same thing over these two lines here. Okay. But the integrand that we're integrating over, the integrand is, let's write it out. What is it? It's 1 over 1 minus e to the minus 2 pi iu e to the minus t minus 2 pi I NBU over 2 sine u lambda over 2 squared. What we want to do now is we're going to turn these two integrals over these lines into a contour integral, okay? So we're going to have, we've got these poles here, remember? What I would like to do is I would like to complete this, join them up as a contour integral by completing this at infinity. Now, I can do that as long as the contribution from infinity is 0, okay? And to show that, I need to show that the integrand vanishes at infinity, okay? Now, it's not so hard to show that, but one can show that this goes to 0 as mod u goes to infinity, okay? And therefore, I can do this closing of the contour. So let me just write it out again. So the integrand, the integration that we have is the integration from, that's the integration in the yellow line going backwards, plus the integration then going out to theta minus, that's these two things here. And then I could add plus an integration over infinity, which is 0. And now this whole thing I can write as a single contour integral. Okay, so now we have, this is the u plane. And all I've done, and now I had this line here before like this, going this way. And now I have this line going this way. And I've joined them up at infinity, like so. And so we have a contour C that's enclosing all of the real axis and going around it anti-clockwise. And along the x-axis, we have all these poles. So let me just write out the final expression, then I'll pause for any questions. So now if we write the free energy, we see that it's actually given by a contour integral. Okay. du over u, 1 over 1 minus e to the minus 2 pi iu. Okay, this factor came from the sum over n. E to the minus t minus 2 pi I nbu divided by 2 sine u lambda over 2 squared. And this is the crucial expression, where C is the contour that goes around the x-axis, all of the x-axes, anti-clockwise. But remember, it doesn't include the 0. So we have to kind of put it together at 0 plus. So it doesn't include the pole at 0. Okay. Not pole at u equals 0. That's not included in this contour integral. But all the other poles are included. So we have to integrate over the whole of the x-axis. Now, this expression is not the same as the Guberkamavafa expression. It's different. But we propose that this is the correct expression of the integrating out calculation. Okay? Are there any questions about what I've explained to get to here? Because this is the crucial, this is essentially the, all we have to talk about now is its implications, but this is the final answer. So I'll pause for any questions in the steps that I took. All right, I'll just repeat those steps again, just so we're sure from our starting point. Okay, so remember, we started from this expression here. That's the expression that we had after we restricted to this alpha 0, 1 equals 1, we had an expression like this here. And now when we did a change of variable, and that meant that we had to change our integration line. So now it was some diagonal line, half line like this in the U-plane. And we have a sum over n. So we have to do this, and we have to sum an infinite number of these integrations, like so. And we could bring all the positive ones together and all the negative ones together, but we can't bring this together with this because there are poles along the x-axis. So we've split our sum over n into two sums. Sums over positive thetas and sums over negative thetas. And then we just did these two sums, the geometric sums, okay? And they gave us the same integrand apart from a minus sign. And so this minus sign is just telling us that this integration over the theta has to be done backwards. So it's going from infinity to the origin. But apart from that, the integrand is the same for both of them. And so as long as that integrand vanishes at infinity, we can just write this whole thing as a contour integral, like so. And so that's the final expression that we have. All right, so that was a little summary. Are there any questions? Oh. Okay, so now we can either take a 5-minute break or we keep going. I don't know what do you suggest, Daniel? Okay. All right, so essentially, this is the main result. We claim that this is the result of the integrating out calculation. And now what I want to explain is how this is different to the usual Guber-Kommer-Raffa expression. So the thing we would like to do, first of all, is look then. So then if we have a contour integral which encloses the full real axis apart from the 0. And so that's going to pick up any poles along the real axis. Okay. And so what we would like to do now is think about which poles are getting picked up. Okay, we're just going to localize onto those poles. So the integral, the contour integral, will localize onto poles because that's what contour integrals do. And so we have to think about what are the poles of the integrand. And we can see that there are two types of poles. Two types of poles. Okay, so there's the first type. The first type is type 1 poles, if you like. They come from this 1 over 1 minus, e to the minus 2 pi iu factor in the integrand. So that's going to give us a pole whenever u is okay, so that's the pole. I'll write this in blue maybe to remind us. Whenever u is a positive integer. When u is a positive integer, e to the 2 pi iu is 1, so that's going to give us a pole. So these are the positive integer poles. And what is going to happen on those poles? Well, we can kind of see what's going to happen. We're just going to be evaluating u at a positive integer. And so we're going to get a sum over positive integers of this expression here, where u is a positive integer. That's in fact nothing but the original Guber-Kommer-Raffa sum. So this will give us terms behaving as, so we have e to the minus tu, but now we're localizing onto integer poles, so e to the minus kt, and we're going to get a sum over k, this kind of terms. Okay, and in fact, those are just this is just the usual Gubic-Kummer-Waffer expression for the resolved conifold. So that's just this thing that I wrote here. Well, I can write it out again, but sorry, here. That's just, it's going to reproduce the usual Gubic-Kummer-Waffer calculation invariance. So that gives us the usual Gubic-Kummer-Waffer contribution to the free energy over those poles there. But on top of that, okay, so let me write it down. These are just the usual Gubic-Kummer-Waffer terms. If you want, these are what are called worldsheet instanton contributions. And so this reformulation of the calculation reproduces all the original results. Okay, it reproduces the Gubic-Kummer-Waffer calculations from the poles at integer values of u. Are there any questions about that? Okay, so we don't lose any information and everything is just the same as before from those poles there. Okay, but the crucial point is that we have new poles now, because you see that we have these poles in the sign here along the real axis when u is so we have new poles, type 2 poles are at u is at 2 pi over lambda times a positive integer. Okay, because then we have this term 2 sine u lambda over 2. That's going to give us second order poles. And because we're doing the contour integral over the whole real line, we're going to pick up all those contributions as well. Okay, so those are new contributions. They were not present in the original Gubic-Kummer-Waffer formula. This is new contributions that we obtained because we're writing this as a contour integral over the plane and picking up all those poles. Are there any questions about those new contributions? Okay, so let's look what
So the initial contributions are counting BPS states, right, in the Calabi-Yau. So is there any interpretation of these contributions, what they are counting?
Okay, let's have a look first of all what these contributions give us. So because now we're evaluating at 2 pi over lambda times an integer rather than just an integer, then now we're going to give these contributions, these will go as now e to the minus tu doesn't go to e to the minus t times an integer, but instead we're going to get a sum over e 2 pi kt, but now over lambda, because u goes like 2 pi over lambda now rather than just an integer. Okay, so that means that these are terms that behave like e to the minus t over lambda, and I already mentioned them in this talk. These are precisely non-perturbative contributions. Non-perturbative contributions to the free energy. These are the things that were missing before, which is why we had to treat it as an asymptotic series only. But now we have the non-perturbative contributions in the expression. Okay, so now we claim that this is in fact the full answer. So this is the main result. So integrating out M2 branes gives non-perturbative contributions, non-perturbative in the topological string coupling contributions to the topological string free energy. And I'll even use an exclamation mark for that, because this is the big new thing that we found. And we see now that this thing actually behaves like a proper function, not just an asymptotic series, because remember before we had a problem precisely when u when lambda took a rational was rational. So remember before we had this problem that if lambda was rational, we were getting divergences. And that's why we couldn't define the function over rational for rational values of lambda. This is what we discussed here. If lambda is rational, then we have divergences because this sign is going to 0. But now there's no problem with having rational lambda. All that happens is that sign is going to 0, but that's precisely what these non-perturbative poles are. So the divergences that we were seeing in the asymptotic expression of the original Gopa-Kumar-Vafa expression are nothing but the non-perturbative contributions that we are now picked up in this formulation. So there is no problems here for any value of lambda. This whole thing is completely finite and gives the full, we claim this gives the full answer. This is the full, at least the so-called holomorphic part of the topological string free energy. Okay. Now, let me just write the final general expression, and then I'll try to answer your question, Daniel, although I don't have a good answer for it. But so there's just one more thing to do, because we just calculated this so far for this special case of alpha 0 equals 1, the so-called resolved conifold. But okay, everything, all the steps that we did, you just repeat. You can just repeat for each term in the sum of a beta and r. And therefore, the full expression for the free energy, now if we sum of a beta and r, just looks like this. d over u. And then we have this 1 over 1 minus e to the minus 2 pi iu. And then e to the minus. And now we can have this beta dot t. And what we call beta dot b. Okay, it's not so important. And then 2 sine u lambda over 2 minus 2r, where beta dot t is what we call beta iti, and n beta dot b is the floor function of beta I bi over 2 pi, which is an integer. So this is the final, so all we did was just put back the sum over the different BPS states. And this, we claim, is the full answer for the integrating out calculation. And it's also, we claim, is the full holomorphic topological string free energy, including the non-perturbative contributions. Okay. So that's really the end result that I wanted to get to. And now we can discuss it a bit and see what people think, if there's any questions. And then we can, well, either decide I could just say a few more words about it, or we can stop, because that's the main thing I wanted to show. Okay, so first of all, what are these guys? What are these non-perturbative contributions? I don't know. There's some kind of topological string instantons. I guess that's what people expect these things to be. But maybe I'll just say a few words about the fact that it was not so unexpected that we should be able to pick up these non-perturbative contributions from this calculation. And we can even have some kind of an interpretation of them. So this will be a little bit of a digression. I can do that. It'll just take me 5 minutes or so. But let me ask first of all if there's any other questions about this result here. Maybe I'll just make a couple of comments then about this result. Note some things. First of all, that the non-perturbative contributions, remember, they come from the poles in this sign, and so they only come from when R is 0. Okay, because if R is bigger than 0, so 1, 2, 3, there's no poles in the signs, and so you don't pick up those poles when you do the contour integral, and so there's no contribution to non-perturbative terms. So the non-perturbative terms in this calculation only come from the R equals 0, and so they only depend on the R equals 0 Gubbicum of alpha invariance. So okay, they only depend on alpha 0 beta. Okay, so that's one thing that we see straight away. There's something else I wanted to say. There's some potential subtlety of whether this sum over beta and R could lead to new poles in this. In other words, if you take the sum and put it into the integral, it could be that doing the summation will lead to some function that gives you new poles. We don't think that that is possible. We've thought about it, but that could be the case. But so we think that this really is the full answer. Though we haven't quite proven it. Yeah, this is all I have to say about this expression for now. Of course, there's a lot of things to say about this, but I don't want to go into it too much details. Let me talk a little bit about a nice physics understanding of what these contributions are, and also why we should have expected that the Gubbicum of alpha calculation does give us non-perturbative effects. Okay, so physics intuition. Are there any questions? No, okay. So the point is the following. We can go back. If you remember in the first lecture, I told you about essentially the first type of such calculation that was done, which was you can take QED and you can integrate out the electron. Okay, so when you integrate out the electron in a constant background field, remember I drew these diagrams of the electron, and then you have photons here, or you can have like 4 photons and so on, 6 photons. And then when you integrate out the electron in the loop, you find an effective action which goes like f squared plus f to the 4 plus f to the 6, which is very, very similar to the calculation that we just did. And this calculation was done in 1936, I think. So this was done in 1936. I believe that's the case, I'm not sure, by Heisenberg and Euler. And the effective action that you get after you integrate out the electron is called the Euler-Heisenberg-Lagrangian. And that's precisely the analog of the calculation we just did. The only difference is basically that we did it in a supersymmetric setting, and also we integrated out an infinite number of charged particles rather than just one charged particle. But also in the background, which is imagine self-dual, but okay, roughly speaking, it's the same kind of calculation. Now, it turns out that you can actually resum all these terms, and the Euler-Heisenberg-Lagrangian then looks a lot not that dissimilar from the expression that we get. You get 1 over sine in that Lagrangian, well, 1 over sine h. And then you get poles, just like we had in our analysis. So you can resum all the terms into a function. I think it's something like cot, you know, something like that, or cot h. How do you write that? Cot like this. This is all, by the way, in the book by Schwartz. You can look it up if you want to. And then you get very similar thing. You get poles at values of the at certain values of the Schwinger parameter. And those poles you can do by contour integration, actually. And it's known what they mean, those poles. Those poles lead to terms. These lead to, non-perturbative effects. These lead to non-perturbative effects. In the following sense, they give you an imaginary component of the Euler-Heisenberg-Lagrangian, which behaves as something extremely similar to what we're finding, 1 over n squared, eta minus n. Now, this is the mass of the electron squared over the charge of the electron, 1 over h bar. Okay, so what do we see? We see we have a 1 over h bar, just like we have a 1 over lambda here. These terms, we have 1 over lambda, 1 over h bar. That means these are non-perturbative terms, just like we had non-perturbative terms in our calculation. And they even go like the mass over the charge. Remember, in our case, the mass is like the charge, since it's a BPS particle. And so this whole thing goes like what we call Z. So this is basically, an h bar is like lambda. So this thing is basically going like Z over lambda, which is precisely, if you want to call this T over lambda, which is precisely the type of terms we're picking up. And so we get those kind of terms already in the 1936 calculation of Euler and Heisenberg. Okay, what do these terms mean there? It was known what these terms mean. What these terms mean is that if you have an imaginary component to the action, that means that the action is decaying in time. Okay, but remember, we've integrated out the electron. So it's just an action for the electric field, and the electric field is therefore decaying in time. Why is the electric field decaying in time? Because it's pair-producing electron-positron pairs, and this is precisely what's called the Schwinger effect. So this is nothing but what's called the Schwinger effect, where the magnetic field is pair-producing pairs of the electrons, and because of that, it's decaying in time. Since we've integrated out the electron, this just manifests as the fact that the action picks up an imaginary component, and so it decays in time. Okay, that's precisely the Schwinger effect. And so what we find is exactly the same thing. You find the non-perturbative piece, which behaves exactly the same thing. So it's the analog of the Schwinger effect. Now, it's not really the Schwinger effect in the sense that it cannot be that the graviphoton field decays in time, because this is a supersymmetric background. Supersymmetric backgrounds have no time dependence, but the physics is pretty much the same. It's the analog of the Schwinger effect now in the case of the supersymmetric calculation. And it's even known that the Schwinger effect does have an interpretation in terms of instantons. So that's just like the new instantons, the non-perturbative instantons that we associated with the topological string. So all we did was actually find the analog of the Schwinger effect, but in this supersymmetric setting. So I hope that this gives you some kind of intuition as to what is this physics. maybe just I'll mention some words about. It might be surprising that you can do a perturbative calculation and get a non-perturbative physics out of it. That's what's done here in the Euler-Heisenberg calculation. Remember, they start from perturbative QED, and they get this non-perturbative contribution. The reason that that's true is that we know that if you have a path integral, if you do something like, if we have a path integral over some UV degrees of freedom, in this case, this is going to be the electron, and some IR degrees of freedom, in this case, it's going to be the photon, okay? In the case of Heisenberg-Lagrangian. And you have, let's do it in Euclidean time, some action that depends, the UV action, which depends on the UV degrees of freedom and the IR degrees of freedom, okay? And then how do we calculate the effective action? We do part of this integration. So we write this only as we do the integration of the UV degrees of freedom, and then we find some IR action, which describes only the IR degrees of freedom, okay? That's what the Euler-Heisenberg calculation is. It gives you an action for the photon only after you integrate out the electron. It's also the calculation that we did. We derived the action for the gravity-photon field after we've integrated out the M2 branes. This integral, if the UV physics you've integrated out is Gaussian, so it's free, it's just quadratic, you can do this integral exactly. Okay, so if phi UV appears only quadratically in SUV, then you get an exact expression, exact integration. We know how to do Gaussian integrals. And if you do the exact integration, then you don't lose any information. You have to get everything. You have to get also the non-perturbative effects. You can't lose any information. You get the full information. Okay? That's why when Euler and Heisenberg integrated out the electron, they recovered non-perturbative terms in the effective action. That's also why when we integrate out the M2 branes, we recover non-perturbative physics. That's just because the terms that you have just appear quadratically in the action. Now, in our case, in the case of QED, this is because in QED, you just have, an electron with, in a covariant derivative, you have something like this. And then this is just a fixed background. So that the action is just quadratic in the thing you're integrating out. There may be higher order corrections. Now, in our case, we don't know the full action. There may be higher order pieces, so it's not just a quadratic integral. But the important point is that only the quadratic piece gives rise to F terms in the low energy effective action. The higher terms in the action, the higher derivative terms, and all the other contributions, they give contributions to things that are not F terms in the low energy effective action. Okay, and when we calculate topological superpartition function, we're just calculating the F terms. And that means we're just getting a contribution from the quadratic piece. And so when we integrate out those states, we're really doing an exact calculation. And when you do an exact calculation, you pick up also the non-perturbative contributions. All of this is already in the Euler-Heisenberg calculation, which is textbook material you can find in Schwartz. So all we covered was basically the same thing, but now in this M-theoretic supersymmetric setting. Okay, so that was my general explanation as to why we expect to find non-perturbative effects when we integrate out these states. So I'll stop now for any questions. I think this is all I want to say.